You know Redis for one thing, right? Speed. We're talking incredible, sub-millisecond speed. It's the go-to in-memory data store for pretty much everything, from caching to gaming leaderboards. But how in the world does it actually get that fast? To figure that out, we have to solve this really fascinating puzzle that's right at the heart of its design. Okay, so here's the puzzle. Redis gives you what we call O of 1, or constant time lookups. That means finding one key out of a million takes the exact same amount of time as finding one key out of 10. It's flat. But it also gives you these hyper-efficient range queries, like find all the users with scores between 1,000 and 2,000. And those run in what's called O login, or logarithmic time. So how can one system be a master of two completely different, almost contradictory performance profiles? Well, the answer, and really the secret sauce behind all of Redis's magic, comes down to a brilliant combination of two foundational data structures, a souped-up hash table and a probabilistic marvel called a skip list. In this explainer, we're going to unpack both of them. First up, let's talk about the dictionary. At its absolute core, Redis needs a way to store a value and get it back by its key, and it needs to do it like right now. This is where the hash table steps onto the stage. The best way to picture a hash table is to think of a big filing cabinet with a ton of drawers. When you want to store something, you take its key, you run it through a function to get a hash, which is basically just a drawer number. You go directly to that drawer, open it, and put your item inside. And when you need to get it back, you do the same calculation, go to that exact same drawer, and pull your item out. No searching required. And the result of that design is, well, it's beautiful. Under normal conditions, this open one-drawer system gives us O of 1, or constant time performance for lookups, insertions, and deletions. This right here is the foundation of Redis's raw, unfiltered speed. But, there's always a catch. What happens when your drawers start to get full and overflow? The simple solution is to just get a bigger cabinet and move everything over. But for a system like Redis, pausing all operations to move millions of items would create a massive, completely unacceptable lag spike. It's the classic stop the world problem, and it's a performance killer. So of course, Redis does something much, much smarter. Instead of that brute force classic rehash where everything just grinds to a halt, it uses something called incremental rehash. And the idea is just so powerful in its simplicity. Don't move everything at once. Instead, with each new command that comes in, just move a few items from the old cabinet to the new one. The system never, ever has to stop. This is Redis's clever solution right here. By spreading out that enormous job of resizing into tiny, bite-sized chunks, it amortizes the cost. No single operation ever feels the full pain of the move, which means your latency stays nice and low consistently. And the result? The effective, or what we call the amortized cost per operation, remains O1. Redis gets that bigger cabinet it needs, but it never has to hang a closed for renovation sign on the door. It's just a beautiful piece of engineering. Okay, so the hash table gives us that blazing fast key lookup. Solved. But what about ordered data? I'm talking about things like a gaming leaderboard or a time series index. Hash tables are kind of like a messy room. Yeah, everything's in there somewhere, but there's absolutely no order to it. For that job, we need a completely different tool. And this is where the skip list comes in. This is so cool. Imagine all your data is lined up in sorted order on the ground floor, like houses on a long street. Now, imagine building a series of express walkways or expressways above it. The highest walkway has very few stops, letting you leap across huge sections of the data. The next one down has a few more stops, and so on. To find an item, you just take the fastest expressway as far as you can, then drop down to the next level to zero in on your target. This structure was introduced by William Pugh way back in 1990, and it's a probabilistic alternative to more complex things like balanced trees. Those express lanes are built using probability. Basically, each item has a random chance of getting promoted to a higher level. The neat thing is, it achieves pretty much the same performance as a balanced tree, but it's often a whole lot simpler to implement. And the performance you get is fantastic, because you can skip these huge chunks of data at every level. Finding an item, inserting a new one, or deleting one takes logarithmic time, or O log n. That means even if your dataset doubles in size, it really only takes one extra step to find what you're looking for. It just scales beautifully. So let's recap. We have two powerful tools in our belt, a hash table for O of 1 key lookups and a skip list for O of log n ordered operations. The final, just absolutely brilliant step Redis takes is to ask, hey, can we have both at the same time? And the answer is a resounding yes. This is the Redis sorted set, or as you'll usually see it, the Z set. It's a hybrid data structure that masterfully combines the hash table and the skip list into a single incredibly powerful tool. So here's how it works. The first part is a hash table. This table's job is simple. It maps each member, say a player's name, directly to their score. If you want to know what score Alice has, you just look her up in the hash table. Boom. It's an O of 1 operation, pure unadulterated speed. And the second part is our skip list. Now, this structure doesn't really care about the member's name at first. It organizes everything by score. And if scores are tied, then it uses the member's name to break the tie. This is the engine that powers those efficient O log n range queries, like get the top 10 players. And this slide right here is where it all comes together. When you run zscore to get a single player's score, Redis just hits the hash table for that sweet O1 lookup. When you ask for a range of scores with zrange by score, it uses the skip list's express lanes to find the start of that range in O log n time. And when you add a new score with zadd, it updates both structures at the same time to keep them perfectly in sync. It is literally the best of both worlds. So, why does all of this matter for you as an engineer or even just as someone curious about technology? Well, understanding these fundamentals isn't just an academic exercise. It's deeply, deeply practical. If you're ever in a technical interview, these are your gold nuggets. Explain how incremental rehashing is the key to avoiding latency spikes in hash tables. Articulate why the Z-set hybrid is so darn powerful. The hash table gives you O1 for specific score lookups, while the skip list provides O log n for range queries. And for bonus points, you can compare skip list to balanced trees, noting their simpler implementation for basically the same performance. So when should you actually reach for this thing? Anytime you need a leaderboard, any kind of ranked list, or even a simple time series index where you need to query by score or a timestamp. In those cases, the Redis sorted set is an incredibly efficient choice. Ultimately, the secret to Redis's performance isn't just about writing fast code in a low-level language. It's about making clever, fundamental choices about how to structure your data in the first place. The Z-set is the perfect example of combining two really good ideas to create one truly great one. And that leaves us with a final thought. Redis made a conscious trade-off. It uses more memory to maintain these two structures side by side to gain this incredible speed and flexibility. And it really makes you wonder, what are the hidden engineering decisions and the clever data structures that are powering all the other tools you rely on every single day?